Some 13.75 billion years ago, the universe emerged from a hot, dense sea of matter and energy. As the cosmos expanded and cooled, it spawned galaxies, stars, and the planets we observe today. But the timeline between when the universe began and the universe we observe today is huge, and there are lots of unsolved mysteries in that period of time. Fortunately for curious minds that want to know how the universe began and evolved, cosmologists have offered a very sharp picture on what the universe's past, present, and future looks like.
Peter Higgs and colleagues predicted that we live in a condensate, so less than a billionth of a second after the universe began. Something happened, a phase transition probably, which caused the Higgs field, Higgs particles if you like, to condense out into the vacuum. The number is that if you asked a naive question, how much energy is contained in that field, the binding energy of this condensate, then per meter cubed, in every meter cubed volume of space, 10 to the 37 joules of binding energy in that condensate. If you do the simple sums, that's more than the energy output of the sun in 1,000 years per meter cubed of space, which should, given our current understanding, blow the universe to bits in a fraction of a second. It obviously doesn't. We don't know the answer to the question why. But if you think about it, it's a very bizarre prediction. It's strange.
For nearly 400,000 years, the entire cosmos was opaque, which means we have no direct observations of anything that happened during that time. As the universe expanded, it cooled off enough to let the plasma become atoms. And for the first time in the history and evolution of the universe, it became transparent. We observe the light from this time as the cosmic microwave background. When the CMB formed, the ordinary matter in the universe transitioned from a hot opaque plasma to incandescent hydrogen and helium gas. Astronomers call this the dark ages of the universe, since no stars had formed yet. Cosmologists use the best observations both to study the dark ages and to find evidence for the first stars in the universe. Only about 200 to 300 million years after the Big Bang, in a period known as cosmic dawn, the first stars began to shine. Although many are population 3 stars, which are a population of extremely massive, luminous and hot stars, with virtually no metals. As the first stars and black holes formed, they turned much of the hydrogen gas in the universe into plasma again, a process astronomers call reionization. But how can scientists be so certain about these events that supposedly happened billions of years ago?
What you're looking at there is an almost featureless and formless universe. The colours correspond to slightly different temperatures in the light, which are really telling you that there are regions which are very slightly denser than other regions in the early universe, but it's almost uniform to 1 part in 100,000. So we're seeing an almost uniform soup. No stars, no galaxies, no large structures in the universe at all, and that is telling us that the universe has not always been the same as it is today. It is not eternal in the sense that it's not always been around with galaxies and stars and planets. At this point in the past, which we can see in the photograph, there were no stars and no planets and no galaxies. The universe was a hot, dense plasma. And that is essentially the clinching piece of evidence, certainly when it was first seen in the 1960s, that told us that this theoretical prediction that the universe was once very hot and very dense was correct. It matches observation. The universe was hot and dense 13.8 billion years ago.
Astronomical and physical calculations suggest that the visible universe is only a tiny amount of what the universe is actually made of. A very large fraction of the universe, in fact 26%, is made of an unknown type of matter called dark matter. Unlike stars and galaxies, dark matter does not emit any light or electromagnetic radiation of any kind, so that we can detect it only through its gravitational effects. An even more mysterious form of energy called dark energy accounts for about 70% of the mass energy content of the universe. Even less is known about it than dark matter. This idea stems from the observation that all galaxies seem to be receding from each other at an accelerating pace, implying that some invisible extra energy is at work. While cosmic mysteries are what push cosmologists forward to work tirelessly and nearly reach a complete picture of the cosmos, there are other things in the universe that are quite well understood, even though they happened a really long time ago. To explain the early universe, its evolution and expansion, cosmologists have come up with inflationary theory. But what is it exactly?
Now, those fluctuations, the different colours, as I said, correspond to very slightly different densities in the early universe. What do they tell us? They're telling us something. These are the seeds of the galaxies. So you stick this, essentially you can stick this into a computer simulation, evolve it forward in time, and you will see, 13.8 billion years later, a distribution of galaxies that matches, statistically, the distribution we see in the Sloan Digital Sky Survey. Again, so matching observation. So the question becomes, if these little overdense regions collapse to form the stars and galaxies, where did they come from? And this is where we start to probe theories back towards the Big Bang, and in a sense, theories of what may have happened before what we now call the hot Big Bang. So if we define the Big Bang as a time when the universe was very hot and dense, we have a theory that tells us how, or predicts how, these small areas of different density could have formed. It's a theory called inflation. The theory is as follows. Before the universe got hot and dense, it was still there, and it was doing something else. It was stretching very fast. It was doubling in size on very short timescales, actually around 10 to the minus 37 seconds, which as you write it out on a piece of paper, looks like this. That's why the theory is called inflation, by the way, because the thing is inflating very fast. The idea is that that inflation is driven by the stuff that you put in the universe. This is central to Einstein's theory of general relativity. In this case, the stuff is something called an inflaton field. It's the kind of stuff that makes the universe stretch very fast. But what was developed was the idea that that smooth sort of ocean, if you like, a field filling space, is not entirely smooth. It can't be. It must have ripples in it. It's not really a still ocean of energy. It's like a stormy sea. And what that does for you when you calculate that is it tells you is that inflation draws to a close, as it must. The universe has to stop expanding at this rate and goes through the hot Big Bang. Then some pieces of space will be stretched a little bit more than others because of the ripples in the energy field that's driving the inflation. Some bits of the universe stop inflating a little bit earlier than others. That leads, when you dump the energy into space and heat it up and make particles, it leads to a slightly non-uniform distribution of particles in the space, which you can calculate from the theory. And when you do that, you find the pattern looks like this, our observation of the universe 380,000 years later. So that's the reason why inflation is, I would say, is the most commonly accepted theory of how the universe came to look like that, which subsequently tells us how the universe looks like it does today.
The pull of gravity began to amplify irregularities in the gas in the universe. As the universe expanded, pockets of gas became more dense and the stars began to ignite. Groups of these stars became early galaxies. About 6 billion years after the Big Bang, large short-lived stars underwent supernova explosions that distributed heavy elements such as nickel, gold, silver, and lead into the universe. Our Sun and Solar System began from a cloud of dust and gas in a spiral arm of the Milky Way galaxy. Our solar system is estimated to have been born a little after 9 billion years after the Big Bang, making it about 4.6 billion years old. Astronomers examine the universe looking for the most far-flung and oldest stars and galaxies to help them understand the properties of the early universe. Similarly, by understanding the cosmic microwave background, they can work backwards to piece together the events that came before. Data from older missions like WMAP help scientists try to solve the most enduring mysteries and answer the most debated questions in cosmology. It is certainly a privilege to be born in the 21st century and have access to all the available knowledge about the universe. Hopefully, if civilization lasts, we will continue to get ever so closely to a complete picture of the cosmos and our place in it. Thanks for watching.